Hello and welcome to the Spatial Structures Movers and Shakers interview series, as we look ahead to the ISS Annual Symposium and Spatial Structures Conference, organised by the University of Surrey and taking place virtually in August 2021. My name is Mark Richardson, and today I'm joined by Lucas Epp, who is Vice President and Head of Engineering at StructureCraft. StructureCraft is a unique team of structural engineers and builders who deliver high-quality mass timber and custom architectural structures. Lucas himself is a structural engineer with more than 15 years of experience working in Canada, the UK, and New Zealand. Lucas's expertise are in complex geometry and structures, and he is passionate about timber engineering, having built a team at StructureCraft of 40 timber engineers and 3D designers hailing from all over the world. Lucas, thanks very much for joining us on the Movers and Shakers interview series today.
Thanks for having me, Mark.
Well, it's a real pleasure to get the chance to speak to you on the series, Lucas. We begin by asking all of our guests about lockdown. How has that been for you in Canada?
Yeah, I mean, it's been a challenge for so many people, this lockdown, not being able to connect with people, both in a personal and a work level. And so it's been a challenge, but we've really seen our team come through it strongly. And I think that's probably resonates with a lot of other people worldwide. You know, the amazing advent of technology has allowed us to work remotely incredibly efficiently and stay connected with people. And for that, I'm definitely thankful. Would have been difficult to get through an event like this even, 10 years ago, when we think about what that would have looked like. So it's great. Here in Canada, we're starting to see things open up a bit, which is really encouraging. And I think we're going to see a slow but steady return to normalcy over the next 6 to 12 months. So looking forward to it.
Brilliant. Thanks very much for sharing that, Lucas. That's great to hear. And as we alluded to, you are a vice president at StructureCraft. Maybe you could give us a bit more of an overview of that organization.
Sure. Yeah, StructureCraft is a company actually founded by my father, Jerry Epp, about 20 odd years ago now. And it's a unique company focused on not only just structural engineering, but also building. So we have a team that builds the structures we design. And that kind of integrated approach to engineering and building provides for some real interesting opportunities to innovate in the structural space. At both a broader structural level, also at a connection level. And so, yeah, I look forward to telling you a little bit about some of the stuff we're working on today.
Superb. We look forward to hearing about that shortly. We also ask our guests about research papers or projects you are currently working on. Maybe you could give us a flavor of some of the things that are happening at present.
Yeah, some really interesting research happening right now. We're actually involved in writing a new software program to automate the kind of engineering through to manufacturing of these timber buildings, which is a really interesting development. We're also going to be, I think in this year's IASS conference, publishing a paper on a series of domes, which I'll show today, which is kind of one of the biggest uses of timber so far to date in China, which is obviously, an incredible builder as a nation. And so to start to see in this climate emergency, China to start to use timber as a structural material is really encouraging, and it's something that we're really trying to push forward there. So I'll talk a little bit more about that today.
Well, brilliant. And to that, Lucas, let's move to the middle section of the interview, which is entitled Your Space, Your Structure. So at this point, I'll hand over the presentation rights to Lucas, who will be sharing on a topic relating to spatial structures for the next 15 minutes or so. So without further ado, over to you, Lucas.
Okay, thanks, Mark. I'll take over and start telling you a little bit about some of the stuff we've been working on. So as I mentioned, StructureCraft, we're a team of engineers and builders. This is our headquarters just outside Vancouver in British Columbia, Canada. But we actually do work right across North America. A lot of our work is in the US and increasingly some interesting structures as well overseas in China and Asia. But I want to start the presentation or the talk about the master builder concept. And I want to do that by taking you guys back through my career as an engineer. As I mentioned, my father founded a company And he really inspired me growing up as to what was possible with not only structures, but from the use of timber as a sustainable material that we have as a renewable material here on our Earth. And just to give you a window into some of the innovations that Jerry, my father, did, he worked on this really interesting space truss, top of the spatial structures. This was one of the first timber spatial structures of its type back in the late 90s, early 2000s. And this is a highly innovative structure, kind of a free form and plan, but a flat spatial truss structure, tetrahedral truss structure, which uses what we call peeler cores. Peeler cores is what's left after you take a big log and you peel it down into veneers, which are used to make plywood and LVL and the like. And once you get to the very center of the log, which is the young juvenile part of the log, that's typically a very weak, unpredictable material, and it's either turned into fence posts or landfill material. And this really interesting spatial structure was based on the concept of using those peeler cores as structural elements, and actually doing a full series of structural testing on the peeler cores to determine their capacities and be able to use them, even though that they're a highly unpredictable material. And connection concepts, how do you take all these peeler cores in a tetrahedral space truss and actually join them together? So here's the concept of the central casting, which allows each of them to be connected in to transfer both tension and compression forces through the elements. So from a very early age, I was exposed to this concept that you could build, and you had to figure out how to build the structures you were engineering. Here's some of the shots during construction on the site. And you can kind of see the yellow and green and red tags on the peeler cores, and that's indicating their load capacity after a extensive testing regime at the University of British Columbia, down with Professor Ricardo Foskey. And so really interesting concepts of how do you advance timber engineering to use a material which would otherwise be close to a waste product in kind of a spatial structure form. So that really inspired me as an engineer. This was before I had even studied engineering. I was involved in some of the 3D modeling and drafting and this type of thing. But this idea that timber could be used to create long span structures really inspired me. After graduating, I then actually moved to the UK and worked for Bureau Happold and in London there, and was involved in a whole series of projects, working closely with Mike Cook, who I believe is also on this interview series. He was one of my mentors and really an amazing guy to learn from, just a wealth of experience and a fascinating viewpoint on how to create innovative structures, which are holistically innovative, not just structurally innovative. I worked on a tower in Kuwait. This is kind of a 300-meter tower with Foster and Partners. Not really a spatial structure per se, but really interesting. This was one of the first times doing CFD simulation back in 2009, 2010 on these tall buildings, all concrete and steel. Not a drop of timber in sight in this structure. And then I moved on to spend a few years on a giant spatial structure in Egypt with Zaha Hadid, which is a steel space truss, the marrow type space truss with all the nodes. And really interesting project, but of course with the political situation in Egypt back in 2010 to 2011, this project went on pause and never actually got built. But so I spent a lot of my time working on steel and concrete structures while I was in London. And this one, the spatial structure for in Egypt, the fact that it never got built irked me. And I as a person really realized I had this longing to actually figure out how do we build, and let's make sure we build what we're ideating. This is another structure I had the opportunity to be part of in the UK while I was there, the Olympic Stadium in London. And I wasn't part of the engineering team for the overall stadium, but simply just for some much simpler cable nets that went across the stadium for the opening ceremonies, which was a fascinating thing to be a part of, almost designing a secondary structure connected to this highly dynamic structure that you're imposing a whole bunch of loads on, and figuring out how to fly the Olympic rings along these cables to the center of this kind of tensile net of cables. And so this was, for me, one of my highlights working in London, because we actually got to build it and we got to figure out and be out there on site as we figured out how are we tensioning the cable nets, how are we attaching things together, how do we make these connections work. So a real neat thing to be a part of, and figuring out how to put it together, and then being a part of the ceremonies there in London. So back to this concept of master builder. So I kind of started my career in this master builder idea, with working with my father and seeing things actually built. And I moved into a consulting role in both the UK and then in New Zealand. And it really interested me to see how our industry has kind of specialized, and we've diversified, and we've segregated as an industry. And so now we have a lot of specialists who know a lot about some things, very specific things, but very few generalists who know enough about everything. And so this idea of the master builder, Eiffel and Brunel and many of those who created their own concepts, they figured out how to build it, they found the money, they acted as their own contractor and their own architect and their own engineer, through to the segregation of trades we saw through the Industrial Revolution, to today, where we have this bifurcation between engineer and architect, and not always, but sometimes. And so where I get really excited is where engineers and architects are working together as a seamless team of designers, figuring out how to create beautiful, efficient, and sustainable structures. So I'm going to take you through a few projects to show some of our thinking around this. This is the series of dome grid shells I mentioned in China, with the Lugan-Meisel Associated Architecture out of Vienna. And they had a concept for creating these timber shells. These are biodomes in China, in Taiyuan, and 3 different environments inside the biodomes: aquatic dome, a desert dome, and they're creating these different climates for the flora that's exhibited inside. And so a real challenge to figure out not only how do you build with timber in China, a country which is so prevalent around concrete and around steel, but how do we bring timber into China, but then also how do we actually build it accurately? How do we manage the construction of a complex timber shell overseas in a country where there is no expertise building such structures? So the geometrical inspiration for this shell came from the idea of a clamshell, and this idea of a dense pattern at the back of the shells and a sparse pattern at the middle. And so I'll show you a little bit of some of the geometry studies that we did early on with the architect as we were coming up with the structural concept for how we actually create this kind of radial grid of glulam elements. And one of the big challenges we had was not only the structural challenge of how dense this pattern of this grid shell should be, but also a manufacturing challenge. How could we ensure that we could get glulam sufficiently accurately fabricated from Europe over to China and fit it all inside a shipping container? And so that actually drove, funnily enough, a lot of the process of the size of the elements, and also the density of the shell, along with kind of some constraints around the glass on top of the shell. And so this idea of using parametric modeling to be able to study not only the timber structure, but also the glass on top, and how do we optimize the glass so we have a minimal amount of doubly curved glazing, although a significant proportion of it still had to be doubly curved from a glass perspective. And then down to the materiality concept. This is a single block glued piece of glulam, which is actually CNC'd into double curvature. And the reason we did that instead of actually pressing it into a doubly curved element is just because the capacity of the manufacturing isn't there to manufacture significant volumes of doubly curved elements. And here you see the concept of these doubly curved glulam pieces prefabricated into panels and then flown into place on the structure. These 3 shells, the largest of them has about a clear span of about 90 meters. And so to engineer these and to optimize these requires, a lot of thinking, not only from an analysis side, but also from the parametric side. And so here's some of our computational models where we're looking at the performance of these shells as the direction of the wind load varies. One of the big challenges was the buckling performance. And so underneath the biggest dome, we had this really interesting series of cable nets. And these sketches are a whole bunch of sketches of some of the guys on our team. How do you connect a series of cables up to a timber shell above? And here's some Rhino modeling of this kind of idea of a casting, which connects the timber shell above to a series of diagonalized cables below. And this casting actually rotationally decouples the cables from the directionality of the timber above. And so these rotationally decoupled cables are anchored onto these castings, which are then threaded onto a giant central rod, which goes right the way through the casting and actually allows us to tension the whole cable net by simply drawing the threaded rods closer to the timber shell above. And so here you see kind of one of the initial prototypes of working at a material scale with stainless steel, of creating this casting and then actually structurally testing to failure this casting. Here you see it in situ underneath the shell. And that cable net actually created another interesting challenge of how do we create shear stiffness between the layers. This is a 3-layer timber grid shell. So this is at our facility here outside of Vancouver, doing full-scale structural testing with load cells to see what's the strength and stiffness of these connections between the 3 layers of these timber grid shells. And so obviously those shells will never get loaded to failure. We actually care about the initial sequence stiffness of these types of tests. So lots of structural testing to prove out our concepts and create timber connections, which hadn't really been done before. Even moisture testing. This is, we're using screws in a highly humid environment. So we got to figure out how are these screws going to perform after the wood's being exposed to very high moisture contents for a long period of time. And so we're kind of doing that moisture testing inside our facility. And here you see the shop drawings. This is, again, all using Rhino. And so we're actually creating all the automated shop drawings for each piece straight from Rhino and sending the CNC files straight to the manufacturers, in this case in Europe. So 2 different manufacturers worked on the CNC processing for the glue lamps, one in Germany, one in Austria. And we sent them directions and exact sequencing for each container of material, so they know exactly where each piece goes in the entire project as they're shipping it from Europe on rail or ocean freight through to China. Now here you see this concept of the prefabricated unit coming together, and this little animation gives you an idea of we're doing prefabricated units, but we're leaving strips in between them to allow for tolerance. This is critical because nothing's ever perfect on a job site. And so you have these prefabricated units which are perfect, but then you have inevitably some dimensional bust between these strips of prefabricated panels. And so we left these infill strips to allow us to join those back together later and make any dimensional adjustments if required. So here you see prefabricating a panel, flying into place up on the shell, and you can see the scale of these structures, almost a 300-foot clear span on the largest of these grid shells. So really interesting exploration, not only from a structural standpoint, but also from a materiality and an erection and an assembly standpoint, which is, ended up creating one of the largest non-triangulated timber shells, as far as I'm aware, worldwide, for the largest dome. Here you see some of the shots inside this dome. And so a really unique visual aesthetic. We see so many of these steel grid shells worldwide. This is one of the most recent modern ones to use timber. We're starting to see it become more of an interest from an architectural standpoint to use timber in places and shells like this, and this symbiosis of the timber shell structure above and the natural flora beneath. It creates a really beautiful environment and something that we were really proud to be a part of. Now I'm going to tell, that was a very large scale structure. Now I'm going to tell a story of a similar approach on a much smaller scale structure. This is actually near Tianfu in China. And this is for an agricultural expo. So locally they're exhibiting what the agricultural industry produces around Tianfu. And so this idea of all these trees, they wanted to create an observation tower which overlooks all of the fields surrounding the area. And so we came up with this idea of a forest canopy, this kind of series of randomly leaning columns, and a kind of a shelter on top, and then a viewing deck at the middle. And we had a certain amount of wood glulam material that we had to use for this observation tower. It had to be built very fast. I think it was from the concept through to almost being built in something like 3 or 4 months. And so we came up with this concept of using these leaning columns to kind of mimic the non-orthogonality of a forest. And on top is what we call nail laminated timber, this idea of boards stacked side by side, and then we're actually warping the nail laminated timber to kind of lift the canopy towards the opening. And so I'm going to show you this little video. This is kind of a video showing the structural and multi-objective optimization we performed to kind of figure out what geometry should these columns take. We don't want them all to be up and down. And we're using nail laminated timber, which in itself is actually a one-directional structural material. It spans in a single direction. But we're wanting to point support, which is creating weak axis moments in the panel. So we set in place a whole bunch of really interesting constraints on our optimization algorithm, where the columns obviously can't hit each other, and then the columns are a certain cross section, because this is the material we have available. It's a 135 by 220 mil cross section. Then it can't be longer than a certain length because of the available materials. Then we also want to minimize the amount of weak axis span. So you can see this is a terrible solution because we're getting a whole bunch of weak axis cantilevering. The panels are spanning left to right on this page. And so we put a constraint on minimizing that weak axis bending. And then we're also saying that the net sum of all these leaning columns must be roughly equal to 0. We don't want a structure that wants to tip over under its own self weight. And finally, we must be supporting the floor structure in a straight line, so that we have this kind of rectangular viewing platform. So then we're doing section checking to make sure the glulams has enough capacity on each iteration check, and then also minimizing the major axis and minor axis bending of the shell, and checking the global buckling. So slowly iterating towards kind of a solution, and this is kind of a slowed down version of the optimization you saw before, where you're investigating hundreds, if not thousands, of solutions, and finally ending up at a solution which globally minimizes all these constraints. And this is a really interesting use of what we call genetic algorithm. And that's kind of an ability to look at a multi-objective solution space, which is very, very complex and is very difficult to optimize with traditional optimization techniques. But with a genetic algorithm, because you're able to accommodate this very kind of choppy solution space, you can get to an optimal solution. And so here you start to see the canopy after it's built, kind of leaning in through the trees, and this idea of these sloping timber columns coming up to this shell, and the sloping of the columns creating these different seating areas and opportunities underneath the tower. And here's the built structure. So a very small scale structure, but an interesting application of optimization techniques, and really came together nicely. And right adjacent to this, we're actually doing our next biggest structure in China, which is about 80,000 square meters. It's a series of vaults. It's an exhibition center very close to that tiny little observation tower. But here we're talking about structures on a much larger scale. This is the largest span is about 115 meters, and the tallest of these vaults is about 45 meters tall. So it's as tall as a 10 or 12 story building. So these are giant kind of almost coverings, and inside these coverings are other buildings, museums and exhibit halls and food halls and the like. And the architect Chui Kai out of Beijing posed us the challenge: could we actually expose the timber to the outdoor elements? Could we leave it exposed and not have to cover it, so that you can see the cladding of the truss structure is actually done on the bottom chords of these triangular trusses, not up on the top. And so our initial kind of structural concept is this idea of a constantly changing triangular cross section, which starts large at the bottom and comes to a narrow point at the top, and creates this ability to resist lateral loads, both in plane and out of plane, for this is a reasonably high seismic zone. And so we're creating this really unique truss structure. And so here you see some of the kind of scale, and this is kind of our 3D model showing the scale of the buildings inside, and then these timber trusses, which basically clear span across the build structures. This is some footage from early on in the construction, where some of these buildings, these arches are getting placed, and we're kind of using this really interesting structural technique of it's not actually a truss. It looks like a truss, but it's actually a Vierendeel truss. And you can kind of see in this picture here, these truss elements don't actually meet each other. In fact, they miss each other by quite an amount. And so this is actually not a traditional truss structure at all. It's actually using moment and shear action in the chords to transfer the forces. And this is responding to the architect's request to minimize, almost make the chords of the truss look like they're not even touching. So we're using steel plate elements as thin as possible to connect the top chords and the bottom chords together and create this very elegant, almost disappearing connection between the top and the bottom chords of these giant trusses. This is one of the largest ones on the structure, about 115-meter span. So this is still under construction, as you can see, but you get a feeling for the scale of the structure. And then finally, I just wanted to show a project which is just going to open up in the next few months in Idaho, which is a basketball arena. And again, in the field of spatial structures, it's all about the concept. We have all these fancy algorithms and fancy tools to do our form finding and to do our form searching, but really what it comes down to is the concept from the architect, the concept from the engineer. What are we going to create? How are we going to create this structure? And this is the initial sketch from Alec, who's the architect on this basketball arena, and he wants to create this beautiful doubly curved shape drawing from the Palouse Hills in Idaho. And so the question is immediately posed: how do we create a roof which kind of simulates that double curvature, that smooth shape shifting that the hills show there in Idaho? And this is the final design as it was come up with. And here we're actually looking at trusses. So we're looking at glulam cords, which kind of follow the swooping, undulating form of the roof, and then steel compression cords, and steel compression webs, and then tension rods as the cords of these trusses. And so then we're looking at optimization as an ability to iterate on the structural shape of the truss to get to a minimum moment solution and reduce the amount of material used in these trusses. And because the solution space is huge, we can have trusses and kink posts at whatever geometry we want. But you can see the difference between an optimal solution and a non-optimal solution is significant. We can save a lot of material. We can design sustainably through use of these optimization techniques. But the optimization techniques are just the tool. You have to have the concept as a designer in the first place. For the clear span kind of across this basketball arena, you kind of see here on the right, we also went through a whole bunch of different concepts of how do you clear span about 130 feet. And you've got about a 200 foot of tributary area coming onto this truss, which spans 130 feet. And so here's some of the initial concept thinking again, thinking about the concept first before you go into the optimization. We landed on this kind of propped cantilever concept here, where we're actually able to integrate the services inside the two chords of this giant truss. So the services for this whole basketball arena are actually concealed inside the structure, so you don't see ducts underneath the structure. Here, this is kind of a detail of this giant portal frame, clear spanning 130 feet. And here we're using this curved column to kind of thrust and creating arching action into the beam, which goes across the arena. And so the big question for us as structural engineers is, how do you transfer about 400,000 pounds of force, or over 2 meganewtons of force, from the timber column into the timber beam? And so we're using this idea of a thrust block, which basically allows us to transfer the load in direct compression. And so here you see the kind of connection peeled back in its gory details of how we actually transfer those magnitudes of loads. And then because we're building it, how do you actually fit these pieces together? So here's in our workshop, test fitting the pieces together. And this is a highly collaborative, where so many people, architects, engineers, designers, carpenters, master craftsmen are coming together to figure out how do we build these, how do we accurately mill them and test fit them. And interestingly, because we're using arching action, the stiffness of our footings really matters. And so the stiffer the footing is, the more arching action we can get. This is kind of a shot of the final 3D model, these giant portal frame trusses which clear span across the arena. And so I'll just skip to some of the shots of the interior. Here you see the structure complete, and you can see some of these concepts of this combination of using timber and steel where they make most sense. So it doesn't always make sense to use wood. I mean, our company focuses on using timber as a sustainable and renewable material, but sometimes it makes sense to hybridize, to use steel as well. And so that's something that we are focused on, is using the right material in the right setting. So with that, I think I'll close and pass back over to you, Mark.
Lucas, thanks so much for taking us through your presentation there. That was a wonderful tour of some of the current projects that StructureCraft are involved in. Particularly enjoyed the 3 projects you showed us from your work in China, and excited to have the opportunity to learn more about that at the IASS 2021 and Spatial Structures Conference. So yeah, thank you very much for taking us through that, and great to see a very innovative use of timber. We've had guests on the series talk about the use of bamboo, but awesome to see another application of a natural material. So yeah, thank you very much for taking us through that. We're now going to move to the final section of our interview, which looks partly to the future of spatial structures, and in particular the 2021 motto or theme of inspiring the next generation. I wondered, Lucas, what advice would you offer to aspiring engineers or architects looking to enter the field of spatial structures?
That's a great question. I think one of the best pieces of advice I can give is find a great mentor, because who you learn from, particularly early in your career, is extremely formative to what you're going to become and the career path or trajectory your career will take. So I think finding someone who's passionate about engineering and about using material efficiently is incredibly important to those who are looking to get into this field. So look far and wide, find the person that's going to mentor you, and then enjoy the ride, because if you find the right person, you'll learn a ton.
Thanks, Lucas. That's a superb answer. Actually, we've not had anyone suggest that, but I couldn't agree with you more. I think that's a really excellent outlook, and yeah, get a good mentor. Great advice. We've also had a couple of questions from some of our audience through social media, so be keen to ask those to you. One of our audience members has asked, after opening the Seattle office and growing on the West Coast, what is the long-term perspective on the US market for StructureCraft?
Yeah, so our company is growing in the US. We already do a significant proportion of our work there. And so I think, expanding into Seattle was a natural progression for our company. But we're seeing the use of timber in the US spiking, just like we're seeing so many other places in the world, and for good reason. And so we're seeing architects right across the US really start to embrace this idea of building with a sustainable material. And that's not just in these longer span structures I showed you today, but it's also in the multi-story, more traditional construction typologies, which are actually where we as structural engineers can probably make the most impact, because that's where the large majority of our built infrastructure lies. And our company is very involved as well in these mass timber type structures. And that's something that, how do we make those more efficient? And even how do we use less wood in these types of multi-story mass timber buildings, because they often end up with these solid slabs of timber, which is great because you're sequestering carbon, but it's still better to use less material. And so that's one of the things we're actively involved in researching and figuring out, use of timber concrete composites, because you often are required by the building code to have these concrete topping slabs from a fire perspective or an acoustics perspective. And so how do you reduce the amount of material overall that us as engineers need to use, is certainly one of the topics we're really investigating right now, and is really important for every engineer out there. How do we reduce and reuse more renewable resources.
Thanks for that, Lucas. And you touched on the issue of sustainability there, which is something we've looked at across all of our interviews. And another audience member has asked, according to one press outlet, the volume of timber projects will double each year for the next 10 years. How is the industry securing sustainable resources against increased timber demand? And might this result in a transition from timber to increased use of lightweight structures?
That's a great question. Timber, first off, timber can be a lightweight structure and is a lightweight structure. In fact, we're often seeing on these multi-story mass timber buildings that we're reducing our foundation costs because the superstructure is lighter. But it's a good question, because now when we're building with mass timber, we're starting to use more wood, and we're harvesting more wood from our forests. And so what does that look like from a longer term sustainable cycle perspective? Are we planting enough trees? Are we sustainably managing our forests? And that is a great question. And the reality is different countries are doing better or worse on that spectrum of managing forests. And there really is a completely wide spectrum worldwide of how that gets managed. But we're seeing a lot of the forward-thinking countries start to take a very proactive stance on, even from a governmental perspective, how forestry is managed. That's certainly the case here in Canada, also in many of the Central European countries. And so the reality is this mass timber movement is still using such a small fraction of the amount of wood that the overall construction or building industry uses, on the order of a couple percent. And so it can grow still significantly without really changing totally the dynamics of the use of wood as we use it from a worldwide perspective. But I think people are already starting to take notice and starting to look at how do we sustainably harvest forests to address the inevitable fact, which is that timber is a renewable resource, and we have to be figuring out a way to use that sustainably for the next millennia. And eventually steel and concrete, we will start to deplete those natural resources. And so I think it's something that each country is addressing slightly differently, but it is being addressed.
Brilliant. Thanks very much for that answer, Lucas. And we've now reached the end of our interview, but thank you very much for taking us through your presentation and for talking to us today. For those watching the Movers and Shakers interview series, a quick reminder that registration for the 2021 conference is still open. So far, we have attendees from more than 40 different countries who have registered for the event. Please do head to the conference website for full details and information. And if you've enjoyed this video, or indeed any in the Movers and Shakers interview series, please remember to like, share and comment. All of your views and thoughts are welcome. But for now, Lucas, it was a real pleasure to speak to you today. Thank you very much for giving us such a wonderful insight into StructureCraft and some of the projects you've got going on. Excited to hear more about that at the 2021 conference. Well, hopefully we'll get the chance to catch up with you then, if not before then. But thank you very much, Lucas.
Thank you, Mark, and appreciate the opportunity to talk to you. It's a great conference, and I couldn't recommend more attending it. It's one of the first conferences I attended as a young engineer, and so much to learn, so many people to meet, and just so much innovation at the conference. So yeah, looking forward to it.
Okay, well, we appreciate that, and yeah, speak to you soon, Lucas. Thank you.